our next topic is going to be on vapor pressures of solutions. And so now we're going to talk about mixtures. We're going to talk about solutions, not pure liquids. So last chapter we did pure liquids. So the idea of vapor pressure is the same, but now we're going to talk about, well, what if we have something like 70% by volume rubbing alcohol, which you can buy in a store? What's the vapor pressure of that solution? What's the vapor pressure of that mixture? We could do the, pure water. We could do the pure rubbing alcohol in the last chapter. We could talk about how they change with temperature. Those trends are still going to hold. Vapor pressure goes up as we heat it up, stuff like that. But now we're going to talk about what is the total vapor pressure of this mixture. What's, what happens as it's mixed? How do we calculate that? And so to do this, what we lean on is Raoult's law. And so the vapor pressure of our solution is going to be equal to the mole fraction times the vapor pressure of the pure substance. And then we're going to just keep adding. Maybe we have a mixture of 2 things or 3 things or 4 things. It's just the mole fraction times the pure vapor pressure. So if it was by itself, this would be the vapor pressure of the liquid. But if it's a mixture, we have to account for everything together. And we encounter mole fractions in 221, but I'll refresh your memory on what they are. But before we do, there's just one more thing I want to remind you of. Or not remind you of, but point out with this equation. And that's that you can also dissolve solids. And they don't have vapor pressures. Solids don't just poof, turn into vapor. And so they essentially have a P0 of 0. They don't have a vapor pressure of their own. And so if you're dealing with a solution that only has dissolved solids, or sometimes there's liquids that are not volatile, they don't have a vapor pressure, so they have a P0 of 0 as well. Then it simplifies down and it's just the mole fraction of the solvent times the pressure or the vapor pressure of the pure solvent. And so then it's just a one-step problem. So you just find your mole fraction of your solvent, multiply it times this number, which you're going to get off a table. All these vapor pressures come off a table. Mole fraction is what you calculate. You multiply, maybe do addition if it's volatile solutes, and you get a final answer. And again, maybe we rearrange it, and there's got to be, we tell you all but one thing, right? That's how it works. So you'd be like, what is the mole fraction? So the example I'm going to work up has a little bit of unit conversion stuff in it, but small price to pay for something you can see in the grocery store shelves, right? I'm sure you all were shopping in the first aid aisle and were like, I wonder what the vapor pressure is on that bottle of 70% by volume isopropyl alcohol, my rubbing alcohol, Everyone wonders, you're like Band-Aids, oh, what's the vapor pressure of that rubbing alcohol? Well, today you get your money's worth, you get to find out. So the first thing you got to do is you got to take these percents by volume, convert them into moles. This is a little bit dicey what I've done here because volume isn't necessarily conserved, but that's a whole other thing. So I'm approximating a little bit, but I just multiply by the density, divide by the molar mass, and boom, I get moles. So you beg, borrow, and steal your way to moles. And then I'm going to add them up, get my total, what's the total number of moles in this solution, all right? And then I'm going to calculate my mole fractions. And so the first one I'm going to do, I'll do the mole fraction of my 2-propanol. So this is my rubbing alcohol right here. So my mole fraction is going to be equal to the number of moles of the substance divided by the total number of moles. And so it's just going to be 0.927 moles over 2.58 moles. And ultimately, I'm only going to get 1 sig fig in my answer. I'm keeping this in my head the whole time. I only get 1 because I only had 1 here. But I'm going to hang on to some digits, avoid rounding errors till I have to. And let's see, that comes out to be about 0.36. Should be a nice unitless decimal. And then I look up my vapor pressure of rubbing alcohol. And as you all already know, it's 33 millimeters of mercury. That's right. The random units of gas pressure are back. You're welcome. It's all coming together, right? All the painful memories of 221. All right, so we've got this, and how do I know what that was? Again, I totally memorized it because I'm a genius. I didn't just look it up on the internet. It wasn't that I was even too lazy to thumb through the book and find it. No. I wrote my good friend Google. I wrote him an email. I was like, Dear Google, what is the vapor pressure of 2-propanol? Cordially, Joe. And Google responded in, yeah, Google's a show off, by the way. It tells you exactly how long. It's like 0.023571 seconds found 2,118 billion results. It's like, okay, Google, we get it. All right, so the mole fraction of water, that's what we're gonna calculate next. So our X of H2O, and we just do the same thing. So it'll be 1.66 divided by 2.58 moles. All right. And you just punch it up in the old calculator and you get 0.64. Now, one thing I'm going to point out right now, I'm dealing with two things. These mole fractions should add to 1, so I could have gotten lazy and just subtracted this from 1 and gotten the same number, but it's always good to work through in case you made an error up here. If you add them up and you get like 5,000, you go, wait a minute, I messed up on the mole calculations. Hold on, because they should add to 1, or with rounding errors, you know, a little bit of wiggle room there. Maybe it's like 0.99. It happens. Happens to the best of us and the worst. Happens to everybody. So, once again, I look up the vapor pressure and I get the vapor pressure of water is gonna be 23.8 millimeters of mercury. Okay, so I look these up online or in the book or whatever, ask your dear friend Google, and now we just calculate. All right, and so my vapor pressure of the solution is going to equal the mole fraction of 2-propanol times its vapor pressure. And I'm going to add to that the mole fraction of water times its vapor pressure. And I will get an answer in millimeters of mercury, also known as torr, because God knows there aren't enough units of pressure. We have to start giving the same ones different names. And it comes out to be 30 millimeters of mercury. Because again, I only get one sig fig, so we're just going to call it an even 30. Manufacturer was too lazy to give me more significant figures on the bottle. And so now you know, when you're going down the Fred Meyer aisle, pretending like you're looking for cat food, but really you're looking for isopropyl alcohol so you can admire its vapor pressure. Now you can be like, oh, that's 30 millimeters of mercury right there. Or, oh, is it a little warm in the room? Maybe it's 31. All right. Or, you know, a little chilly. Maybe it's like 27. Who knows? Who knows? All right. But at standard room temperature, 30 millimeters of mercury. There you go. So now you'll be a hit at all the parties. And now if there was a dissolved solid, so both of these are volatile liquids. They both have vapor pressures by themselves. But if it was a solid or something, you know, there are liquids that don't have a vapor pressure because they just, or it's negligibly small. So we say they're non-volatile. Then you would just have to solve for the mole fraction of whatever has a vapor pressure and go from there and just multiply and add up. And if it's only the solvent, then you get this beautiful situation where you don't have to add 2 or more pieces together. You just solve one thing and you're done. All right, so that's the story here. You know, no crazy enthalpy diagrams, no delta H's, just a little bit of math. Got to remember how to find mole fractions. That's probably the worst of it. And, you know, you can have a little bit of adventure getting the moles. Just be aware of that. And, you know, we're going to talk about freezing point depression and boiling point elevation